These are the area samples. Why is the personal data very high, then low, and then higher? There is a reason. And they wanted to do a study on cleaning. Yeah, cleaning is like maintenance. It's one of the dirtiest operations. It's to be expected. This was lactose. It's non-toxic, so it's not a big issue. But here is the statistically random array. Background samples. This is around the filter dryer. This is around the glove box. Here's the mean. Here's the standard deviation. One standard deviation. Backgrounds. Day 2. This was day 1. This was day 2 in the morning. This was day 2 in the afternoon. The backgrounds were, statistically, they weren't any different. It was other than this one here. Here are the data points that we got from the 3 studies. There's the first one. We had problems bursting the bag and so forth. There were reasons why it was not a normal operation. We videotaped everything to be sure that we could replicate what and analyze what was going on. But here's the second cycle, and here's the third cycle. Very comparable. So why is the operator seeing a higher exposure here than he did here? Statistically different. Very simple. He's the guy who charged the reactor in the first place on the first day. He carried the contamination with him into the equipment. At the end of the first day, late in the evening, we'd finished, but we decided to prepare ready for tomorrow. So he charged the filter dryer for tomorrow. Following morning, he came in clean. Went in, we did our first study. Put it out, we charged it again. Now he's getting slight exposure. Not as much as the first day, but slight exposure. He is the source of the contaminant in the room, because the statistically random data here is so consistent compared with this data here. Those are the 2 data points. Here's the variable, not the equipment. The actual hardware emission, because we knew the volume of the space, we knew the average air concentration in the space, was approximately 3 micrograms of lactose was released to the entire room during the study. We have a confidence factor of 2 studies of 98% because we were able to pull the data. And we came up with this functional containment factor. Containment factor, let me explain that. We had to contrive something as a reference base. It's a contrivance. Knowing that we have a 3% dustiness index for lactose, we have 10 kilos of lactose in there, we'd like to stay with a single unit. We figured if there's 1 kilo of, if we express there's 1 kilo of friable dust available to the surfaces of that device at the release points, that's probably about as good as we'll ever get. So based on that, how much did we let into the room? How much was the challenge? We come up with a factor of 30 million as a containment factor, plus or minus 1.5 million based on our standard deviation. With a glove bag, you should be able to achieve at least 1 million isolation between the inside and the outside. With a glove box, you should be able to achieve a minimum of 10 million. And with a well-engineered box and good training of operators who will follow the procedures, you're probably up into the 100 million or billion fold range between the inside and the outside of that box. Far better than the nuclear industry tries to do, by the way. Analysis of variance excluded the first cycle, and our confidence factor of overall for the 32 pooled samples that we had was 98%. Statistically robust data. So we were far better than what is allowed in the US as 1,500 for a PPE protection factor. I gather you guys are limited to 200. They'd like to get rid of PPE, obviously. The cultural contribution is evident from the work practice of the informed operator. That is a key. The operator is the biggest failure of any testing that you do. The operator did release the lactose from himself, and the measurement of difference between the operator and our data around the equipment was a factor of 10 to the 3 different. And we're actually measuring in our performance tests far better than any of the environmental folks have ever tried to do for things like dioxin, phthalate esters, estrogen disruptors. I mean, Rudy Boozer and Chris Rappier in Switzerland and Sweden have done some fabulous work, but still they're only in the part per billion range. And here we're talking harsh petroleum with our testing methods, way beyond practices that most people ever do. So we're on the learning curve here. Thanks, Michelle. I'll leave it to you.
What we did was, we did a milling glove box, we did a dispensary, we did a lot of different equipment for this facility. It was a pilot plant. It had no previous containment or PPE requirement. They'd say it was an airplane hangar. And so we went through and talked to the operators, worked with the client to make sure that, you know, what they needed, what the requirement was, what the process was, which is really critical because you need to get the operators involved at the very beginning of the design. And that's something that I'm kind of plays into the containment level because the operator is the factor that can make or break your containment system. So that's how that relates to the operator exposure limit. So we did some drum enclosed systems. This is a large dispensary discharging through a split butterfly valve. You can also change that and go to a continuous liner system or even a Hecaflex or something like that. You can use different types of methodologies off of the glove box itself. So you can build in flexibility. Again, it goes back to a split valve and then also some other different types of equipment. These are all standard designs, but the most important thing is whenever you're doing a full containment system is that you have a mock-up, you understand the process, the product characteristics, if you know what those product characteristics are, and you also need to get the operators buy-in. So we usually do these huge elaborate mock-ups. We bring the operators in, we leave a clipboard attached to the mock-up, and we leave the mock-up there, and we walk away. And then we let the operators come in and make their comments about that mock-up. And the reason why we do that is because then they don't feel intimidated about, you know, if I make this comment, is it going to sound stupid? Or is this, you know, I really don't want anybody to know that I'm asking this really stupid question. So they have the ability to make those comments on the clipboard, and we come back and review them, and then we bring them all in again and go over it. And you'll find that once you do that, the operator's going to buy into that, and they think that they've actually designed it or helped design the glove box. And so then their practices and their utilization of that containment piece is much more effective. And I think that's critical. So here shows another charging isolator inside of one of our OEL level testing tents. And so we'll set up a series of these. So here's the filter dryer without all of the manifolds and things on it. So we did the whole process. We did the filtration and drying, the dispensing, and went through the whole thing like that. So I wanted to give more time for Brian to answer some more questions on his method of OEL level testing the engineering capabilities of the hardware rather than, you know, just the operator effect. So I always call it the operator effect because it doesn't make a difference. Milling, that kind of thing. So there's kind of an overview of the equipment we supply: a milling glove box, a dispensary, filter dryer, split butterfly valve, and then a separate system for co-milling.